Hello, everyone. Welcome to a new session of our Gamma seminar. Sorry for the delay. We had some technical issues, but we are now ready. And it is my pleasure to introduce Javier de Lucas from the University of Warsaw, who will give us a gentle introduction to Dirac manifolds. So Javi, the floor is yours.
Thank you, Xavi. So as the title says, this is just a gentle introduction to Dirac manifolds. So it's going to be a very basic introduction to the topic from the very beginning, surely repeating some things, but since this is now also a subject of the University of Warsaw, it's nice to have some introductory stuff for undergraduate students. So this is the aim of this thing. So don't expect any really new things, any research from the very last years. It's just something very basic about how Dirac manifolds appear, how they look like, which are the properties, and so on. So, so how these Dirac structures appear? Well, essentially, Dirac structures appears at the time when presymplectic structures and Poisson structures were very well known. And in the spirit, partially in the spirit of generalizing previous geometric structures, Dirac structures managed to describe as particular examples presymplectic manifolds and Poisson structures. Moreover, Dirac structures, they contain a so-called Dirac bracket, which allows one to retrieve the very famous Dirac bracket found in theoretical physics. So these structures had interesting properties, generalizing those of previous structures while appearing in important physical topics. Indeed, you can find Dirac structures to describe non-holonomic mechanical systems. You can use Dirac structures to describe integrable systems, as I will do in a while. You can use Dirac structures to make a lot of stuff. Yeah, so it's by itself is a topic very interesting. And so, as I said, the applications I will to develop, I will fix this talk about an introduction about the mathematical properties of Dirac structures. As an application, I will describe the system because I know that some of you are interested on that. And I will explain a little bit how they appear in this topic. But pretty much, the ideas can be pretty much used to general so-called integral system with coalgebra symmetries or things of the sort. So it's many of the things you will find for symplectic geometry can be developed and can be generalized to more general differential equations, which are Hamiltonian with respect to Dirac structure. So, okay, I will start briefly from the very beginning, from something that most of you know, but some don't. So recall that a symplectic manifold is nothing but a manifold N along with closed non-degenerate to form omega on the manifold N. There are several manners to understand that this is non-degenerate. One of the manners is to understand that at each point you can define a certain mapping from the tangent space to the cotangent space to the point in such a manner that the application making the contraction of the form with a tangent vector, this is an isomorphism. This is one of the manners of understanding that the differential to form is non-degenerate. You see that you have here a vector, tangent vector, you have two fours, so the contraction of that two four with the tangent vector is just a covector. And this application is obviously linear. So if this is an isomorphism, so we will say that omega is non-degenerate. Of course, here during the whole lecture, I'm just focusing on the case of N being a finite dimensional manifold. Okay. manifold would be finite dimensional, connected, all this stuff. So there is another manner of saying that a two form is not degenerate, and is by saying that there exists a certain n, it can be 0 or a positive natural number, in such a way that this is a volume form. Okay, both manners are equivalent. The first one is the sum of this traditional one, and it's very useful for things that will be common. The second one about the volume form is one that it is, well, short, and it doesn't need any much explanation to see how it works. Okay, so I will be talking about Dirac manifolds. One of the things I will be interested in mainly is about Hamiltonian systems, about application of this to integrable systems, or co-integral systems, to Hamiltonian systems in general. So one of the main analyses I need is about Hamiltonian vector fields. In the realm of symplectic manifolds, a Hamiltonian vector field is a 13 vector field in the manifold in such a manner that the contraction with the symplectic form is minus the differential of a function. Okay. Of course, some of you use this minus, some of you don't. The key is that there are two main schools about Hamiltonian vector fields. There is one school, mathematical school, who prefers the minus because some objects will be pretty much well defined mathematically. They will be nicer. And the other way of approaching this is from geometric mechanics, from the physical point of view, where this is a plus. Anyhow, please think that everything will be up to a minus plus sign at certain moments. Don't care much about that. It's a technicality. You only have to take care of this minus at certain places. So you see, if you put this in here, the talk will be a little bit more mathematical at 13 points. So when you have a 30 Hamiltonian vector field, and it's related to some function f, we say that f is a Hamiltonian function for x. Obviously, it's not uniquely defined because you can sum a 13 constant to the function. It will be also Hamiltonian for the same Hamiltonian vector field. Meanwhile, the other way around, vector field is uniquely defined by means of the function, because the contraction of a differential 2 for a symplectic 4 with a vector field is a isomorphism. So if the contraction is this, which is fixed for a certain function, there is only yes vector field satisfying this condition. So given a vector field, you may have different Hamiltonian functions, but given a certain Hamiltonian function, you have a unique Hamiltonian vector field, and there is always a 13 vector field. Okay, so vector fields, the space of vector fields, Hamiltonian vector fields for a symplectic manifold, it's a Lie algebra. It can be proved. It's quite simple, and maybe we did it in the past, that if you pick up the Lie bracket of two Hamiltonian vector fields, the bracket is again a Hamiltonian vector field. Yeah, this is one thing we need. Okay, so the thing is that when you have a 13 symplectic manifold, there is a 13 algebraic structure related to the symplectic manifold, which is very interesting. This is a Poisson algebra. In algebraic terms, a Poisson algebra is nothing but a vector space, okay, with a certain linear product. Normally, it's a product, and it's assumed in general that it is commutative, okay, and bilinear. And you have also a Lie bracket such that when you fix the 13 element of A and you leave the second part free, this mapping is a linear mapping that is a derivation with respect to the product. This just means that if you have two elements B and C of A, the product, the bracket, the Poisson bracket with the product is like here, like this, yeah? It's nothing, is this. So, for everything ABC belonging to A. The thing is, a Poisson algebra is an algebraic structure, and it appears very naturally when you are dealing with a symplectic manifold, because every symplectic manifold, the space of function on the manifold can be endowed with two operations. One is the dot that represents the product of function, the standard product function, that it is bilinear or bilinear, yeah, and it's commutative. And the second thing is a 13 bracket that is defined by means of the symplectic fold in this manner. You pick up two functions, yeah. For every function, I said that you can define a unique Hamiltonian vector field, and you can do the contraction of the symplectic form with these two vector fields, and obviously this gives you a function. Okay, and it can be proved that this is the same as applying the Hamiltonian vector field xf on the function g. Of course, for some of you that come rather from physics, from geometric mechanics, normally this appears with a minus. But as I said, it's everything up to a minus, a plus sign, so don't care much about that. The thing why mathematicians like more this way of defining things is because when you consider the Lie bracket of two Hamiltonian vector fields, the nice feature is that this is a new Hamiltonian vector field, as I said before, but also the function related to this new vector field is just the bracket of these two functions. And this appears in this mathematical approach. In the geometric mechanics approach, a minus appears, and it's not that nice. Mathematicians don't like it as much because the following proposition doesn't exactly hold. I mean, the following proposition says that every symplectic manifold induces an excess sequences of Lie algebras in this manner. Okay, so here you have the zero, you have here R. This is just the inclusion of the zero into R. This is just the inclusion of the numbers, real numbers, as constant functions on the space of functions. And then what you have is a map which maps the function, every function, to its Hamiltonian vector field. This mapping is linear and it's well defined. This is uniquely defined, but it's not injective, as I said before, because different functions with different constant have the same Hamiltonian vector field. So in general, this is not injective. In general, yeah, apart from trivial cases. And the kernel, if n is connected, is R. The reason why this happens is that two can be proved that two functions have the same Hamiltonian vector field if and only if the difference between both of them have a differential which is a constant. I mean, the function is a locally constant. If the manifold is connected, this locally constant is just a constant, and you think R. If your manifold have different connected parts, K, so you should have here to add K, essentially. And this is the way of doing this. So you see, the kernel of this is just given by the image of R. There's the constant functions, and this functions is a surjection, okay, because the image are Hamiltonian vector fields that by definition they are the image of something that comes from this space. So here you have the projection to zero, and this is exact because the image of this mapping BW, the omega, is yes the kernel of the projection that is gives the whole space. So you have 13 of this stuff. So when generalizing these things, what you have is that from a symplectic manifold you obtain a Poisson algebra. But the thing is, when you have a 13 Poisson algebra of this type, one wonders whether every Poisson algebra comes from a certain symplectic manifold. And the answer is a big no. Not every Poisson bracket of this sort is such that the bracket can be written by means of a symplectic form. So here, the Poisson manifold appears, and we will define a Poisson manifold as a pair given by a manifold N and a certain Poisson bracket of the space of functions on N. And that's all. I mean, as everything you say to describe a Poisson manifold. Yeah. So the thing is that when you have a certain Poisson manifold, this bracket is a Poisson bracket. When you fix the first part of the bracket, you obtain a derivation because it satisfies the line, the property. So this behaves like a vector field, and it happens the same about the second factor. So it turns out that this bracket is a two derivation, is a b derivation on its factor. What means that there exists a bivector field. I mean, something that for every point in a manifold gives you some linear combination of stereo product of antisymmetric tangent vectors. Okay, so these are derivations, can be considered the derivations. So when you have this thing, okay, there exists a unique bivector field lambda in such a manner that this is satisfied. The thing is that this bracket is something that it is algebraic. So in differential geometry, of course, algebraic objects can be interesting, but we prefer things we can think of geometrically as vectors or submanifolds or things of this sort. So we frequently prefer this object to this one. We prefer to describe Poisson geometry by means of a bivector field, a so-called Poisson bivector, than using this bracket, this Poisson bracket. Now, the thing is, the fact that this is a b derivation, it tells you that you have a bivector field, but the Poisson bracket satisfies other properties. I mean, these properties are that it satisfies it's antisymmetric, yeah, that it is a bivector, and the other one is that satisfies the Jacobi identity. So somehow we have to encode in this bivector field the fact that the Poisson bracket satisfies the Jacobi identity. And this is done by means of the Schouten bracket, the Schouten-Genius bracket. Okay, so I will explain this in detail. I think we never did. It's something that it appears in geometric mechanics and differential geometry quite frequently. So yes, give me a second to describe it for a while. It will be also useful afterwards. So when you have the space of multi-vector fields in a manifold, normally is written in this manner, okay? These are multi-vector fields. Okay. You want to describe a third-time bracket, a third-time antisymmetric, or symmetric, well, a third-time bilinear mapping, Schouten-Genius, that goes from here to here, and it has a third-time properties. These multi-vector fields, there are 0 vector fields. These are functions. 1 vector fields, they are standard vector fields. Bivector fields are things that at every point I like this. 3 vector fields, and so on, and so on, and so on. So you know that you have the standard bracket of vector fields. The way of describing the Schouten-Genius bracket is by generalizing the bracket of vector fields. If you consider 2 vector fields here, the Schouten bracket is just the Lie bracket of these vector fields. It was like that. A little bit more generally, if you consider bivector fields, they are stereo products of 2 vector fields or more of them, you can always consider the Lie derivative of this multi-vector field with respect to x. indeed, this is just a kind of tensor field. So you can do the standard Lie bracket, Lie derivative with respect to x. So the Schouten bracket generalizes the Lie bracket of vector fields with multi-vector fields. Okay, so in this manner, you can see, for example, that when you have two vector fields, the result is a vector field. Okay, when you have certain, for example, k vector field, that is a contravariant k tensor, this is also a k vector field. This is said, can be said that is a section of the K bundle of the manifold. Okay, this is just that it for k vector fields and vectors it gives a gift of fields. And the thing is, this structure, the Schouten brackets, is generalized to things more general. In particular, when things of this stuff, this part, there are also multi-vector fields. And there is a manner to do it in a nice way. Okay, and the way of one of the manners to define it is by means of this definition. Okay, so you see A is an R vector field, B is an S vector field. Okay, and you can define the bracket. And now you can say that you have this expression. Okay, and here you have R minus 1 vector field, the stereo product of R minus 1 vector field. So this is an R minus 1 vector field. Here you have an S minus 1 vector field, because you know when you write the hat in here, means that this is deleted from the sequence. Okay, so here is state of R, you have R minus 1. Here in state of S, you have S minus 1. And here you have an additional vector field that is given by the pairing from the first vector field and the second vector field that were missing. Okay, you have here. So you see that here you have an R plus S plus 1 minus 1 minus 1 vector field. So if this belongs to this is a R vector field, and this is an S vector field, the Schouten bracket of this is contained in R plus 1 minus 1 TF. So if you have vector field, the standard vector field, this will be R1 as 1 minus 1, it gives you 1. Yeah. You can, if you have a vector field at the beginning in R equal to 1, the result is 1 plus S minus 1 is S. So the result of applying this to a S vector field would be an S vector field. The thing is the description of the fact that lambda in the definition of the Poisson structure comes from bivector field can be described quite nicely by means of the Schouten bracket, because if lambda comes from Poisson bracket, it turns out that Schouten bracket, Schouten homogeneous bracket is equal to 0, and it works also the other way around. If it's equal to 0, you can prove that you can define a Poisson bracket by means of the expression for the lambda. So that's why Poisson manifolds are described by means of n with the Poisson bracket or by means of n and the vector. So the thing is, this Schouten bracket has several properties. And interesting, the first one is not in general antisymmetric. Okay, it depends on the order of A and B. Yeah, it depends on if this is a 1 vector, 2 vector, 0 vector, or whatever. Okay, so you have this expression, and you can see that this expression here, it depends on this. This is called the order of the multi-vector fields. Multi-vector field. You know, if you have a vector field is just 1, if it's a bivector field is 2, and things like that. So the analogous is that these relations, the Jacobi identity, the antisymmetry, and the Leibniz rule, they are changed by means of a certain factor, which depends on the degree of the vector, multi-vector fields. Yeah, there are, you say, this expression like the standard Jacobi identity. This is like the standard Leibniz rule, that it happens that when two elements, for example, B and A, change the order at the beginning, one index appears, one sign appears. Okay, depends on it. This is the general idea. So now, in the case of Poisson geometry, you can define Hamiltonian vector fields in the following manner. That you say that X in a manifold, a Poisson manifold, N is a Hamiltonian vector field if there exists a function on the manifold in such a manner that the action of the vector field on the function is the Poisson bracket with F with G. Okay, or for some F. Okay, and F is called the Hamiltonian function for the Hamiltonian vector field. Alternatively, you can say that a Hamiltonian vector field is so when you can contract the Poisson bivector related with the Poisson bracket with the bivector field to obtain the X. It's exactly the same as before in this manner. Okay, so it turns out that Hamiltonian vector fields are those that belong to the image of this thing, this lambda, yeah, and they are given by the differential image of the differential of a function. Again, you can say the space of Hamiltonian functions of a Poisson manifold is the algebra, and the fun thing, the interesting thing is that now it happens that there are functions, non-trivial functions, for which the Hamiltonian vector field is 0. And this didn't happen in the case of symplectic manifold, when in symplectic manifold, when you had a function and the Hamiltonian vector field was 0, it was just because the function was locally constant. Here, no, they are not. There are functions that are not locally constant that give you a certain Hamiltonian vector field that is 0. This space is called Casimir space. Okay, it's the Casimir of functions, or the Poisson bivector, and as well as in the Poisson manifold case, you will have a new sequence, okay, of Lie algebras. But now, in this place, when you map every function to the Hamiltonian vector field, that it is unique because you don't see if you have this function, this is a derivation, and there is just one vector to define the function. Okay, the kernel of this thing are just the Casimir functions of the manifold. So it's before we have here R. So when the Poisson bivector, when the Poisson structure comes back from a symplectic manifold, appears here R, and when no, you have this more general thing. Okay, if you want a very simple example of a Poisson manifold, you can have R3. Okay, you can consider the coordinates x, y, and z, and you can. Oh, sorry, what happened? Okay, and you can consider, for example, this vector field. When you do the Scouten bracket of this with itself, it gives you 0. The coefficient is not 0, and this vector field is combined by itself. So the bracket, the Scouten bracket version we gave before the bodices, and if you contract this with this z, for example, it gives you 0. So this is a Casimir. Okay, so as I said, you can imagine for a vector field, as I said, every covector gives you a vector field. When you have a certain lambda bivector, Poisson bivector, you can define a certain distribution, okay, given by the image of these operators and the Hamiltonian. Okay, it's defined in this way, and it turns out the characteristic distribution of this Poisson manifold is integrable. I mean, it's a generalized distribution indeed. This means that the rank of the distribution varies from point to point, but at every point you can always have a third manifold whose tangent space is exactly the characteristic distribution, the image of this operator. So when you have a Poisson manifold, what you have is a third foliation by a symplectic manifold. And the thing is that it's not a trivial result that under quite general assumptions on the foliation, a generalized foliation, when you have a foliation of a manifold by means of presymplectic manifolds, what you obtain is a Poisson structure again. So this is a nice geometric way of describing Poisson manifold, that you have a certain foliation of, or it is said normally stratification more technically, but the idea is that you pick up a manifold, you divide it into submanifolds of different dimension, such that every such submanifold is a symplectic manifold. So that means that the rank of the distribution have its even dimensional at every point, but it can be different from 0. So you see, a Poisson manifold geometrically is just a third-time stratification, is a third partition, let us say, without many much details, of a manifold into symplectic submanifold. So there is more thing. I will explain it quite quickly, because otherwise I will do anything about Dirac manifolds. That a presymplectic manifold is something similar to the symplectic manifold, but just asking omega to be just close. Okay, anomalies also require that the rank of the omega must be 0. I mean, do you remember that we defined something of this sort? It is required that the image of this, okay, it will have always at every point, if you pick up an x, the same rank for every x, okay? And this is said that the omega is regular. So this is a technical condition, okay? Sorry, it should be a minus. And this is a presymplectic. So you can repeat everything you had previously. You can define Hamiltonian vector field, the space of Hamiltonian vector fields, the Lie algebra. You can define, again, a Poisson bracket, but the difference here, okay, is that when you have a presymplectic form, this omega, okay, the rank is not all the space. This mapping in the presymplectic case from Tn to T star n is not an isomorphism. So that means that if you have a 13 function and the differential does not belong to the image of this, there will be no Hamiltonian function related to this function. So it's different from symplectic geometry because there are 13 functions for which there are no Hamiltonian vector fields. Okay, so when you have presymplectic manifold Poisson and symplectic, you see third-time limits. In particular, you have Poisson and you have presymplectic. For Poisson, you remember that every function is a Hamiltonian vector field, but it may happen that non-zero function will be 0 Hamiltonian vector fields. Okay, in presymplectic geometry, it happens that 13 function will not have any Hamiltonian vector field. On the other way around, if you have a 13 function and it has a Hamiltonian vector field, the Hamiltonian vector field doesn't need to be unique because omega is degenerated. So you see, in Poisson geometry, given the function, the Hamiltonian vector field is unique. Okay, and in here, in this case, when you have the Hamiltonian function, the Hamiltonian vector field is not uniquely defined. So this relation between functions and vector fields starts to be more and more general. At the beginning is 1 to 1 up to a constant. Then there are less Hamiltonian vector fields, the functions, and here it's absolutely general. So anyhow, the thing that you have to take into account in this case is that there are Hamiltonian vector fields, with a thorough Hamiltonian function. For example, if you have that this vector field belongs to the kernel of omega, in the presymplectic case, it may happen that this is equal to 0. So you may have a non-zero vector field which has a 0 function, okay? These sometimes I call gauge vector fields. Okay, there are vector fields with a 0 function. In Poisson geometry, we have non-zero functions with 0 vector fields that we call Casimir. Okay. Here, as I said, not all the functions are related to Hamiltonian vector fields. The functions that are related, I call admissible, and this span a space called the space of admissible functions. And now the exact sequence we had before, now it's even more complicated, because when you have a certain admissible function that it's not everything, yeah, and you pick up the Hamiltonian vector field is not uniquely defined. So to construct a function, you have to divide by the gauge vector fields, because two Hamiltonian function as symplectic structure coming from the same function, the difference between these is a gauge vector field. So you have, this is even more general. So you have Poisson geometry, you have presymplectic geometry, and now you want to generalize both things. So the way is doing this manner. Remember, Poisson manifold is a stratification by means of symplectic leaves or symplectic submanifolds. And you have here presymplectic submanifold. So the idea to generalize these is to consider a manifold which is a stratification by means of presymplectic manifolds. And this is the main idea of Dirac manifold. A Dirac manifold is essentially a manifold that can be divided into presymplectic manifolds in a way that they can be glued together in a certain manner. To describe this, we need to go further. We have to go to create a new space called the Pointryagin bundle of a manifold, or it is called the generalized tangent bundle. I mean, when you have a certain manifold, you have two objects. You have the tangent bundle, you have the cotangent bundle, and you can construct the direct sum of both of them. Okay, so at every point of the manifold N, this is nothing but the direct sum of tangent vectors with cotangent vectors, with covectors. Yeah. So this is, so in the literature it's called the generalized tangent bundle, the Pointryagin bundle. It has 13 names. Okay. The thing is, this structure contains simultaneously vectors and covectors. Now, to describe as particular cases geometrically symplectic, presymplectic, and Poisson manifolds, we are going to describe something here. The main point is that in Poisson geometry, every differential of a function was related with a certain Hamiltonian vector field. Yeah, this was in this manner, and it can be done always. In presymplectic geometry, the thing was a little bit more difficult, yeah, and certain differential, certain vector fields could be written as the differential of a certain function, okay? But you know, the thing is that it was a little bit different, because in Poisson geometry, out of this, you could determine this part. In presymplectic geometry, out of this, by making the contraction, you could determine it. So in Poisson geometry, you go this way. In presymplectic geometry, yes, you go this way, and in presymplectic geometry, you go this way. And you have these pairs of things, okay? So the idea of Dirac structure is this relation between differential of functions admissible and Hamiltonian vector fields to describe them as subbundles of here and looking for certain properties. So, okay, indeed, you can consider these pairs, they span the image, the graph, let us say, of delta, and in the presymplectic, this was so-called graph of this mapping, okay, these both together. So, you know, for Poisson bivectors of presymplectic forms, you will get some subbundles of the Pointryagin bundle. And what it happens in Dirac geometry is that Courant and others, they characterize which subbundles of things like this, they come from these both things, and eventually more general ones. So this inspired them to define what is called an almost Dirac manifold. So an almost Dirac manifold is a pair given by a manifold and a third time Lagrangian subbundle of the Poisson bundle. You know, you have this. You have to remember that the rank of this is twice the dimension of n, and you have a pairing. When you have a vector, covector, these are the elements of this Poisson bundle. The only thing you have to do is just to contract every covector with the vector of the other pair in this manner and to add. Yeah. So when you have this pairing, isotropic subbundle is one with this bundle. This bundle is equal to 0 balances, okay, on elements of it, and it is called Lagrangian when its dimension is the largest. The dimension is the largest since this is non-degenerate when the rank of L is just the dimension of n. So an almost Dirac manifold is a subbundle or rank the dimension for the manifold, okay, such that this pairing balances on elements of it. And indeed, in the case of the symplectic geometry, when you have things of this sort, this, okay, for example, you have a section of this type, and you can have a section of this type. What you got by doing what it was written above, it just was to contract this with this with this, okay, for example, and you will say that well, it's up to the definition you want to use. It may be with the isotropy, with a Poisson bivector, with the symplectic form, you will get this, and you immediately see that the isotropy of this subbundle on things of this sort, in the case of the Poisson or the presymplectic, gives you that it is equal to 0. So in these cases, presymplectic to Poisson, it turns out that section of this type, generated by them, are such that this pairing is equal to 0. But this is not enough to ensure that this L comes from a presymplectic fold, so directive fold. You need some kind of additional condition to ensure, in particular, that your subbundle is going to come from a presymplectic or a Poisson manifold. And this is done by means of the so-called Dirac, the Dorfmann bracket, okay? And this is just an expression. It's a bracket that is defined on the space of section of Poisson bundle. And when you have two sections, the Dorfmann bracket, it should be there, sorry, is such that the vector part of it is just the Lie bracket of these two vector fields, and the covector part, the differential one-form part of it, is given by means of this expression. This is the Lie derivative in terms of the vector field of the second one form, and this is the contraction with the second vector field of differential of the third one form. You see immediately that this bracket is not antisymmetric, because when you change the first section with the part section, okay, the result does not change by a sign. So in general, it's not antisymmetric, but it has one good thing, is that it satisfies the Jacobi identity. Why we use this kind of weird? Well, we use it because it turns out that in calculations, it's very easy to work out the Dorfmann bracket, and many things can be easily proved by means of this. There is another approach that is called the Courant bracket, okay, and is another bracket defined in space of sections of the Poisson bundle. The part in the vector fields is exactly the same, but the part in the differential forms is antisymmetric in this case, but it does not in general satisfy the Jacobi identity. And in practice, I found, at least in the applications I studied, that this is much difficult to apply. It's the other one is normally easier. Anyhow, if you have an almost Dirac structure, both of them coincide, and on the almost Dirac structure, when it's integrable, okay, both of them they give rise to a Lie bracket and what is called a Lie algebroid. Okay, so the thing is, when you obtain, when you have a certain almost Dirac structure, you have said something that it is Legendre with respect to the pen, and it's integral with respect to the Courant or the Dorfmann bracket. It doesn't matter which one, because on almost Dirac structure, both brackets coincide and give you a Lie bracket. If the distribution, the Dorfmann structure, the subbundle is integrable. The thing is, when you apply this, you can obtain things that are satisfied by means of Poisson bracket and by means of presymplectic force. Indeed, if you apply this expression to a subbundle generated given by the graph of a presymplectic manifold, these things satisfy if the differential form is closed. And if you define a certain subbundle by means of a bivector field general, this will be integrable if and only if the bivector field is a Poisson bracket. Yes, a Poisson bracket Poisson bracket, Poisson bivector. Yeah, and you have these things. So when you have an L, what you can prove is that if L comes from a bivector, things of this, they are of the form div plus a differential one form plus a vector field, this type. And when this comes from an omega, it will be things given by an x in the contraction with the thing. And if it's integrable, this means that it's equal to 0. This is integrable, this means that it's equal to 0. And now, this bivector field can be proved that it exists, okay, when the projection onto the cotangent space is a surjection. You see that's, sorry, this should be theta. Yeah, now it works, and now it works, yeah. So you see that here you have any one form, so the projection of these things onto the cotangent will be a surjection, and it comes from a presymplectic form when the projection onto the tangent is a surjection. So when you have this subbundle, if the projection onto the cotangent is a surjection, you will have certain bivector, and this bracket with itself will be equal to 0. When the tangent, the projection onto the tangent will be a surjection, you will have a presymplectic form, and it may happen that the projection are between two. It can be this case, or something in between. But if it's something in between, it would be something different. There are many other cases. So naturally, you say that this justifies that you have to study the projection with respect to rho, the projection R star that is projected to the cotangent, and there is a fine thing. And the thing is, you can define certain kind of presymplectic form in a certain special manner. So I will go with both things in a while. The first thing you have to take into account when you have a Dirac manifold is that when you have this Dirac manifold, you have the N, the manifold, you have the subbundle, and now if you project the subbundle onto the tangent space, you will get a certain generalized distribution. Okay, something that it's something on the tangent space to N that at every point has a different rank, and it turns out that it's integrable. It turns out that the submanifolds, the integral submanifolds of this distribution are presymplectic leaves, and are presymplectic leaves with respect to this thing, this two form, and how it looks like. When you have one of these leaves, this presymplectic, please remind that the tangent space is generated by means of 13 Hamiltonian vector fields. Yeah, this is the thing, the projection, because you have at the beginning these things. Yep, and you will have something of this type. And what you can do is just to consider that this vector, when you put it up in the distribution L, it can come from something like this, or in general, it comes from a third time vector covector. So if you define the covector, okay, you can consider this as a covector in this distribution. And this gives you a mapping from the tangent space to the characteristic distribution to the cotangent space of the characteristic distribution. This thing, it can be proved to be a real symplectic form from this leaf, and it can be proved that it is independent of the covector associated to this vector. It's well defined, and this is well done. Indeed, by means of this thing, you can construct on the space of function on this leaf a third time bracket that it is what it is called normally the Dirac bracket in theoretical physics. Okay, so this structure is what it gives you, this Dirac bracket, but it's introduced geometrically. So the thing is, when you get this Dirac manifold, as I said, you have the characteristic distribution. When you have the characteristic distribution, the leaves, they are presymplectic manifolds, and they give you a foliation, or more generally, a stratification of the manifold into presymplectic forms in such a way that these presymplectic forms, they can be glued together. The other way around, it works too. If you have a third foliation or stratification, because the leaves are of different dimensions, and you have a 30 presymplectic form in such a manner that you can glue them together to form something like an omega, something like this. You can obtain a Dirac manifold. There are several technicalities about this thing of going from the Dirac structure to the foliation by presymplectic manifold. They are related to the notion of a stratification. They are technically involved, and they are quite subtle. You have to take care of the definitions, because if you don't fix exactly the definition, it happens that a Dirac manifold gives you a stratification by means of presymplectic manifolds, but a stratification by means of presymplectic manifolds does not give a Dirac manifold, but it's just a technicality. There is a counterexample done by Eduardo Martinez many years ago, but it was proved by means, I think, the ratio Ortega, that it was technical and defined everything properly. You could go from one, you could do the converse. So the thing is that now there are lots of theorems about Dirac structure. There is a big amount of work dealing with generalizations to Dirac structures of the things you know from symplectic Poisson, presymplectic geometry, things like integrability, things like the Booth theorem, things like I don't know, Poisson, Hamilton structure, mass dimension reduction, integrable systems, whatever. There is a really big deal of it. So the thing is, one of the things is the Booth theorem. The Booth theorem tells you that if a Dirac manifold is regular enough, regular means normally that the characteristic distribution is regular distribution around a point, has with the same rank. The projection onto the cotangent of the subbundle has also a constant rank. There are things of this type. You can find coordinates in such a manner that the Dirac structure is generated by these vector fields. This looks like the Hamiltonian vector fields related to a third time Poisson structure or symplectic structure even. Okay, these things, they look like gauge vector fields, because you know they are vector fields not related with a Hamiltonian function, with a third Hamiltonian function, like in presymplectic. And these, they look like functions Cm that are related to a zero vector field, like Casimir functions. That's why these are called Casimir functions. Here, these vector fields are called gauge, and these P, Q, are called the Abel's coordinates. Okay, and in this basis, okay, the bracket structure can be written as a matrix of this, the symplectic form can be written in this manner. And you see, you recognize this from I'm sorry, this was the pairing. This is the pairing. You recognize this from symplectic geometry, and this thing is due to this and this. You know, with respect to the pairing, these things, they are constant. They are integrals of these functions. Something like this. So that you have a certain kind of thing of this one. Okay, so I'm past the time, but let me tell you a couple of things more formally. Okay, and I will explain you how Hamiltonian vector fields, Casimir functions, and K-vector fields are defined. And in Dirac geometry, the thing is, when you have a Dirac structure now with a subbundle, a function is called admissible relative to this Dirac manifold. Is the vector field plus the differential belong to the space of sections with the Dirac structure. It's, you know, it's a copy, yes, of this. What happens, for example, on Poisson geometry, on symplectic geometry, when you have certain Hamiltonian vector field, you have the differential of the function and the vector field put together. Yeah. The F is called admissible because, as I said, in this case, not every function can be related to Hamiltonian vector field. Okay, so that's why it's called admissible. The space of Hamiltonian vector field is defined by Ham and Al. The space of admissible vector field, admissible function is defined this way. Okay, Casimir functions of this structure, sorry. Okay, Casimir functions, they are functions related to a zero vector field because there are sections of this type. And gauge vector fields, they are vector fields related to a zero Hamiltonian admissible function. So they are elements, sections of the structure of this type. Normally the space is defined by G and R. The space of admissible functions admits a bracket, that this is just a bracket induced by means of this thing, the symplectic form. Okay, the space of Casimir is an ideal. Okay, it's like what happens in Poisson geometry, but you have to restrict to a certain subspace of functions. The crazy, the initial extra sequence is defined this way. In symplectic geometry, here you have R. Like in Poisson geometry, you have Casimirs. In presymplectic geometry, the Hamiltonian vector field wasn't uniquely defined, so in Dirac geometry, it happens also the same. But considering this, I consider as you can generalize this. I wanted to finish this with a third-time system that is quite well known. It's the sparse equation. Okay, it's essentially this is called the sparse bracket. No. Okay, sparse bracket. It appears in integrable systems. Appears also in string theory, and it has several applications in meromorphic functions. It's a nice topic to study. Okay, this thing is called the sparse equation, which is written. If it's written like a first order differential equation, it's a first order differential equations in the second tangent bounded to R, or this is diffeomorphic to R3 of this manner. So the thing is, the right-hand part can be written like a time-dependent vector field, that it is a linear combination of three vector fields closing as SL to R Lie algebra. Okay, indeed, you can use this to study many of the properties of sparse equation. You can describe it by means of the so-called Lie systems. This thing is explains that it is a Lie system. And the funny thing is that these vector fields, Y, 2, and 3, span the tangent space to R3. I mean, so, you know, in symplectic geometry, there is no manner to consider like Hamiltonian vector fields, all of them together, because in symplectic geometry, Hamiltonian vector fields take values in a generalized distribution, which is even dimensional at every point. But these vector fields cannot be Hamiltonian, all of them together, because they span the total space, which is all dimensional. So there is no symplectic structure turning these vector fields to Hamiltonian. But you can use a certain presymplectic form given by this, and this presymplectic form tells you that all these vector fields are Hamiltonian with these functions. And you can use a Dirac structure to define that, say that this system is Hamiltonian with respect to this Dirac structure, because it allows you to tell for every t the vector field, time-dependent vector field for a fixed t is a vector field is Hamiltonian. Okay, so in this case, this thing and the properties given for Dirac structure allow you to describe the properties of this system. There are lots of things you can do with this. Okay, for example, you can make Dirac reduction. You can to perform a mass dimension reduction of Dirac structures, and you can use this to reduct, for example, integrable systems. And the other thing I wanted to tell you as to finish is that Dirac structures contain as a particular cases all the geometric structure. For example, Jacobi manifolds are particular cases of this, and contant manifolds, they are particular cases of this. So Dirac structures, there is a very big family of structures containing as particular cases contact manifold, 30 cases, or Jacobi manifold, presymplectic structures, Poisson manifolds, and all this stuff. And okay, so this is everything I wanted to tell you. Thank you very much for your attention. I hope that this was somehow clear and it was interesting to you. Thank you very much.
Thank you very much, Javi, for this nice introduction to Dirac structures. Are there any questions or comments? No?
Yes, please. Hello.
Yes, go ahead.
Okay, good evening. Hello, Javier.
Oh, Narciso, hello. I didn't see you.
Yes, just a question. Is there any application of Dirac structures to field theories?
Truly speaking, maybe there are. So I think I have seen something, but it's for field theories. What it's more interested than this is higher order Dirac structures that it will be in a couple of weeks. Those structures appear. Okay, they can be used to study quasi-symplectic, polysymplectic, and multisymplectic and things of this sort. So for higher order Dirac structure, for sure. Dirac structures by its own, I think they have seen several examples. Indeed, using the Dirac bracket, but I'm not pretty much sure. I should take a look. I think that yes, okay, but I think that it is the higher order is quite natural. I mean, when you do the higher order, you get the first thing you obtain is multisymplectic, and when you have multisymplectic, you have the way to do anything. So that's the thing. Thank you.
Okay, thank you very much.
Any more questions or comments?
This thing that you commented about the integrability of the characteristic distribution for a Poisson structure, is there a converse result? Namely, if we have a bivector field whose characteristic distribution is integrable, does that imply that it's Poisson or something?
No, it implies that it is twisted Poisson.
Okay.
But normally, the result that is known is that you have to add some regularity condition. It is believed that maybe there is something in general, okay, more general for not integrable. But if you have a vector field and it turns out that the characteristic distribution is integrable and the characteristic distribution is regular, then it turns out that the vector field is related to a twisted Poisson. I think that is a result by Paula theorem maybe, and by how's this guy from Mexico? Naranjo, Luis Naranjo, I think it is.
Okay.
It appeared in a paper about non-normic systems, and it was written the results I told you, I think it was left like open problem, quite difficult to see what happens if you remove the regularity condition. But one has to take care about technical stuff, okay? Because as you said, here I didn't want to go into details describing stratifications in general, and all this stuff, but it's quite easy to obtain a counterexample if you know define things properly.
Okay, thank you very much.
Thank you, Chef, for your question. Okay, Rafael Azuaje has a question on the chat, I guess.
Hello, thank you very much for the talk. My question is on the case of presymplectic manifolds. Is the Poisson tensor defined on the whole manifold?
I mean, when you have a presymplectic structure, when you have the presymplectic, I mean, you cannot define a Poisson vector in the case you have a presymplectic form. Yeah, this is the first thing. So in general, you cannot define it. Other thing I could say is that the only thing you know is that if you have a certain foliation by presymplectic submanifolds, you have to give up to a Dirac structure. These presymplectic forms of each leaf, they have to be glued together in some manner. And I don't remember the technical conditions, but they are not easy to implement. This is the only thing I can tell you. But as I said, when you have a presymplectic, you will not have a bivector of any type. Yeah, and the only thing about the Dirac structure is you have to go from the leaves you have with each one with the presymplectic form, and somehow you have to put all together. When you have presymplectic leaves that's and you have a regular foliation, it is easy, okay, to see that you can build up a Dirac manifold, but the problem arises when you have a non-regular distribution with points, for example, a point with some submanifold that are, for example, balls, essentially topological around this. So the way of, well, the point is easy, but if you have something more general than that, it can be difficult. Indeed, the original works by Courant and Dorfmann, they use other tensor fields. I mean, when you have this thing, you will think about certain free tensor, contravariant tensor fields, it was. Somehow, if a means of this, you do this more easily. Okay, but anyhow, it's quite tricky. I hope that answers you. It answers your question.
Okay. Oh yes, thank you.
You're welcome.
So are there any more questions or comments? No? Okay. So thank you again, Javi, for this nice talk. And just let me say that next week we will have some kind of second part of this talk where Roberto Rubio will talk about higher Dirac structures. This will probably answer Narciso's question too. And well, you will get the abstract and the title in the usual email. So see you all next week. Thanks for attending.
Thank you. Thank you all for attending. Xavi, we can talk for a second?
Yeah, sure.